Okay, we're going to start chapter 5 today, and I feel like this point on you get a little bit of relief from stoichiometry. I mean, there's still a little bit, don't get me wrong, it's not like it disappears, but it's not just, a ton of stoichiometry thrown in one chapter. So I think basically the rest of the semester, it's a little bit of a break from the math and everything. Um, Correct me if I'm wrong. Totally let me know if I'm wrong. But I really feel like at this point, um, things should be looking up. You won't be so bogged down with 1,000 steps in stoichiometry. And I mean, honestly, I like stoichiometry. I know a lot of people don't. But I mean, it's very straightforward. It's the same thing every time. So there's not a whole lot of things they can get you on. Um, but if you don't like stoichiometry, you're probably like 90% of people. You're not in the 10% like I am, which is fine. But you'll get a little bit of relief. So I think you'll appreciate that and like that. So let's go on to chapter 5. Here we're going to learn about gases. We've kind of learned about gases before. Remember, gases, they have the highest entropy, meaning the most chaos because they can move around the most compared to like a solid, or a solid doesn't move at all. A liquid moves some, but a gas, moves wherever it wants. It takes the shape of the container and the volume of a container. So if I put a gas in 10 milliliters, like a 10 milliliter beaker, it'll have a volume of 10 milliliters. But if I put that same gas in a 100 milliliter beaker, it'll then have 100 milliliters because it expands. It's expandable, unlike solids and liquids. Okay, so let's look a little more into it. So now we're going to get our physics cap on, if you want, and look at pressure and force. So pressure is the force exerted per unit area by gas molecules as they strike a surface around them. So basically what that means is if you put a gas molecule in a container, every time it hits a container, it exerts a force, and that force is called pressure. So anytime basically a gas molecule bumps into something, it causes pressure. Okay, so let's think about, and it has per unit area. So let's think about what all this means. Let me pull up my sketchbook and go back to PowerPoint too. Okay, pressure is the force per area. Okay, so let's think about what this, how this could be affected. How can we increase or decrease pressure? Pressure exerted depends on, one, the number of particles. Okay, so let's think about that. We have this container. Let me draw a container. Excuse my drawings. Okay, this is a container. And let's do another container. Okay, this one's worse. Whoop. Oh, golly. Okay. Anyway, it's the thought that counts, right? Okay, let's say we have some gas particles in here. Let's put like 5. 1, 2, 3, 4, 5. But in this one, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Anyway, you get the point. There's more. Now, where pressure is when one of these molecules hits the container. Okay? Does it make sense that since there's more molecules, it has a greater chance of hitting the container? I think I said there's 13 molecules in here, so there's 13 different molecules that hit the container, versus this one with only 5. So the pressure is greater in here because it has a greater chance of hitting, the container. So the more molecules you have in a container, the greater the pressure. Okay, let's look at another one. Temperature. Okay, think about boiling water. Okay, when you heat something, it increases the energy. Think about the water, and it's got, before it's boiling, it's calm, and then it gets to that boiling point, and it's going crazy, right? Well, gas is the same way. You heat it up, and it goes crazy, and it has all this energy. So it's colliding everywhere. So now these particles, I don't know why this keeps going away. Let's put some, let's see, increase temperature. Now these particles are like zoom, 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 zoom. Yes, they do make that noise all over the place, okay? And because they have so much energy, so it increases the pressure because now they have a greater chance of hitting the container. Remember, hitting the container causes pressure, so anytime we can increase the chances of that happening, we've increased pressure. So increasing temperature and increasing the number of particles increases pressure. Now let's look at volume. Volume says the smaller the volume, increased pressure. Okay, let's see what they're talking about there. Okay, so let me draw two more containers. Let me just draw two new ones. Okay, let's say I have a container, boop, this size, okay, and then a container this size. Okay, we put my gas particles in here. Let's put the same amount, okay? 1, 2, 3, 4, oops, that wouldn't show up very good. 5, 6, 7, 8, 9. Okay, now let's put 9 in here too. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, now remember, the higher chance, we want to hit the container that causes pressure. Now let's look at the volume. Do you see that these have a lot of space here? Okay, these don't have a lot of space. So do you see that? It's more likely that these are going to hit the container first before this one, only because the container is so small, they have nowhere to go. So, I mean, they barely have to move, and they hit the container, causing pressure. These have a lot of room to move, so it's going to take a longer time for it to hit it. So, because it's smaller, they're contained in this smaller volume, the pressure is going to increase. Okay, so let's summarize what we have here. We've learned that if we increase the molecules, that are in the container, increase temperature, remember that causes the molecules to go crazy and hit everything, and then decrease volume. Volume because, we make it smaller. Imagine if we have a lot of molecules in here, we increase the temperature and put, a small volume, they're going to go everywhere. They're going to be hitting everything, okay? And so that's what's going to affect pressure. And that will lead us into our ideal gas law. Let me just kind of show this to you, because we have PV equals nRT. Okay, so let's think about the things that affect pressure. So this is pressure right here, pressure. See, volume affects it, so it's in our formula. N is moles. M is like, a way of saying molecules. So this is moles, so this is your molecules. And T is temperature. Don't worry about R right now. We see it has all of the ways to affect temperature. Alright, let's look at some basic units. Common units, we have a millimeter of mercury. Sometimes a barometer is in millimeters of mercury. That equals to 1 torr. You might have heard of atmospheres. 1 atmosphere is 760 torrs. The average 1 atmosphere is the average pressure at sea level. Okay. There's a Pascal. Okay. That's 1 Newton per meter squared, and this is 1 atmosphere is 101,325 pascals. There's inches of mercury, not to be confused with millimeters of mercury, and pounds per square inch, or PSI. Those are all units of pressure. And so you might have heard of all of these. You've heard of an atmosphere, maybe a torr, millimeter of mercury, or PSI. These are just all ways of saying I measured energy, okay? Just kind of like, you can measure distance in inches and centimeters and meters and kilometers. Those are all units of distance, okay? And they'll mean, essentially the same thing, whatever you get for kilometers is going to be the same distance you get for millimeters, right? You just have it in a different unit. Anyway, so there's just different ways of expressing it. So let's just kind of do one conversion really quick. So 132 psi into millimeters of mercury. So we have, just do it down here. 132 psi. So remember, we're going to have to put psi down here because we want to cancel that out. We're trying to get to millimeters of mercury. So let's look at our units here. Here's a PSI. It says 1 PSI is 1 atmosphere, and we're getting to millimeters of mercury. Let's write all these down. So 1 atmosphere is 14.7 psi, 1 atmosphere is 760 torr, and 1 torr is 1 millimeter mercury. Okay, so we have, I'm writing over here, use a different color. 1 atmosphere equals to 14.7 psi. 1 atmosphere equals 760 torr, T-O-R-R, and 1 torr equals to 1 millimeter mercury. So those are the same. A torr and a millimeter mercury are the same thing, actually. So let's see what we have. We have a PSI, and no other unit has a PSI here, so we need to use this conversion. So we're going to put down here 14.7 psi is 1 atmosphere. Okay, but we want to get rid of atmosphere, so we're going to put atmosphere at the bottom. We're trying to go to millimeter mercury, but so far we don't have one. We have 1 atmosphere is 760 torr, and we can convert that. So let's do that. We have 1 atmosphere, 760 torr. And what we could say is, do you see that? A torr is a millimeter mercury. They're the same thing. So let's just say a torr slash millimeter mercury, because they're the same unit. Do you see a torr equals a millimeter mercury? Okay, so if we multiply this out, 132 times 760 divided by 14.7. So I get, let's see, 6,800, and we'll just say 24 millimeters of mercury. Okay? So that's just a unit conversion, same as like inches, centimeters, and stuff like that. So hopefully this gets you started on pressure and gas. And when we're looking at gas, we're mainly going to be looking at pressure. Like what are the different ways we can measure pressure and calculate it and everything. So in our next vodcast, I'm going to go over a few of the gas laws, if you want, and introduce those to you.